Hello, this is Magic 063, Differential Manifolds. I'm Dm Kchm, and this video is about 2 or 3 examples showing the different ways in which manifolds can present. So first of all, and perhaps most basically, there's curves and surfaces in R3. So, for example, R, vector R, a function of t, t is a real parameter, perhaps restricted to an open interval, and x, y, and z are smooth functions of t, so differentiable of all orders, and therefore all the derivatives are continuous. But that's not enough to get a manifold, or indeed a submanifold of R3. You also need the regularity condition, which is that the derivative is never zero. Non-zero for all t in the domain of R. And that ensures that there's a non-zero tangent vector, and that means that there's a well-defined tangent line. In abstract terms, that'll be the tangent space. If you've got a point, say an isolated point, at which the derivative is zero, then it's sometimes possible to get a concept of tangent line, but in general not. And indeed, if you've got an open interval where the tangent is zero, then, well, in fact, you've got a straight line, so you don't really need manifold theory for that. So this is a standard and stand-in example for curves in R3. And then think about surfaces, or a surface patch. X, y, and z, functions of u and v. Again, everything's smooth. Partial derivatives all exist and are continuous. But that's not enough. The regularity condition here is that the two partials, first of all, are non-zero, and their cross product is non-zero. So they generate a plane, the tangent plane to the surface, and that in abstract terms will be the tangent space. That's for all u and v in the domain of R. Before I move on, I ought to say briefly that although these do give you submanifolds of R3, they are, or can be, rather tricky submanifolds. We'll talk about submanifolds in general much later, but different authors use the words in different ways. And regular curves and regular surfaces in R3 can be fairly badly behaved submanifolds. But they are nonetheless examples of smooth manifolds. And another thing, with the curve, the parameter is often significant. This may be the position vector of a particle, or the center of mass, or it might be a velocity vector. In that sort of physical situation, the parameter is important. But with surfaces and higher dimensional manifolds, usually the parameterization is not important. Indeed, the whole concept of a smooth manifold is that one is looking at properties that are independent of the choice of parameter. We'll go on to that very soon. Okay, let's turn the page. This takes me a couple of moments. There. So another way in which smooth manifolds present is as zero sets. So I have a function, say from Rp, let's make it Rn to Rq, and f inverse of 0 is the set of points of Rn that get mapped to the zero vector in Rq. And again, of course, f should be smooth, So all the Q component functions must be smooth functions of the variables in Rn. But again, there's a regularity condition. And that's on the derivative matrix. I talk about a derivative matrix. A lot of people will say Jacobian matrix. I prefer to keep the word Jacobian for the determinant in the square case. This notation here is for y as a function of x. So that's the derivative matrix, and the condition is that the rank of D must be maximal, must be equal to Q for all points that are actually in the zero set. And if you've got that condition, then it's a theorem that the zero set is actually a good submanifold of Rn. And you can calculate the tangent spaces very quickly. The tangent spaces I won't quite put an equal sign. We'll come back to the precise formulation later. The null spaces or the kernel of the derivative matrix. And so since f has maximal rank at points of the zero set, the nullity of the derivative matrix is n minus q, and the dimension of the zero set is n minus q. And of course you can regard this in different ways. You can say that you've got q smooth conditions on Rn, and you're looking for the set of solutions, and you want to know when the set of solutions form a smooth submanifold, and this rank condition is the condition that you want. And by the way, these zero sets are better behaved than the curves and surfaces in R3 that we talked about a couple of minutes ago. You don't get the bad behavior with zero sets that you can get with the parameterizations. Well, those examples have all been subsets of R3 or Rn. Here's an example that doesn't present as a set of points in a Euclidean space. It's going to be the set of all the oriented lines in R2. And you can see in front of you a circle with its center marked. We'll come to that in a minute. But before we go to that, by an oriented line, I mean the obvious thing, a straight line with an orientation, and I'm assuming that it extends to infinity in both directions, though of course I just write it as a finite segment. And all lines in the plane, all oriented lines in the plane, they don't have to go through the origin. They can go in any direction. And of course, for each line, there's an opposite line. Let's do that in this sort of yellow color. I'll put the opposite head on. It hasn't come out terribly well, but it'll be okay for now. So each oriented line has an opposite oriented line with the same underlying set of points, but the reversed orientation. So this is a very large collection of objects, and it certainly isn't a subset of R2. Okay. So now I'm going to denote that set of oriented lines by a script L with a subscript 2 because it's the plane, and a tilde to indicate that there's oriented data involved. Now I'm going to show that this set of oriented lines can be described analytically in a very clear-cut fashion. So I'm going to use this circle. We'll take it as the unit circle centre the origin. And I'm going to take any oriented line such as that. And I'll call that L. Now the first thing I do is move it parallel to itself so that it goes through the centre of the circle. Okay, and I'll call that L prime. Of course, that is in itself an oriented line of the plane, but what I'm doing at the moment is actually transforming L into a pair of vectors. So now I look at where the L prime intersects the circle. There are 2 points, and I take the one that is further along in terms of the orientation, and I call that vector from the centre of the circle to that point X. And now I'm going to draw the tangent line to the circle at the point X. Okay, there's my tangent line. Okay, now I look at the vector from X to the point at which the tangent line crosses L. So that's there. And I call that vector Y. Okay. So I've now got 2 vectors. I've started off from L, and from it I've constructed an X and a Y. Both vectors are now 2. X is a unit vector because the circle is a unit circle, and x dot y is 0 because y is perpendicular to x. So next page, I'll write that up there. I've got a map. I won't give it a single symbol from L2 tilde to a set which I'm going to call K2. It'll be the set of all those pairs xy in R2 cross R2 such that the norm of x is 1 and x dot y is 0. And I'll call that K2. This is just a temporary notation for this video. And now I claim that that's a bijection. In other words, if I do the reverse construction, if I start off with a point X, I'll do it roughly in the same place. If I start off with a point X on the unit circle, and I take a vector that's tangent to the circle at that point, that's not too bad, that's y, then I can take, perhaps let's change colours here for a moment. I can take the line which passes through the centre of the circle and x, and I orient it from like that because I want the point x to be further along the line in terms of the orientation. And then I come back and I move this blue line parallel to itself so that it passes through the end point of y. And that's my oriented line L. So I've gone now from the pair xy in K2 and I've got an oriented line. And you can check that that really is a bijection. So that's definitely quite a step. We've now got pairs of vectors. In fact, we've got a subset of R4. And I'll show that as a subset of R4, this is the zero set of a smooth function and that the regularity condition holds. So let's move on to the next page. And the obvious, we want K2 to be the zero set of a function, and it's going to be in R4, and there are two conditions. There's the unit condition on X and the dot product condition on Y. So that's two conditions. So what I'm expecting is a smooth function from R4 to R2, and the natural thing to define is that I take a pair of vectors, any two vectors in R2, and I map them to mod x minus 1 and x dot y. And for that f, the zero set is indeed K2, but of course that's not smooth, so let's make it mod x squared. It's now a smooth function and it has the same zero set. And I'm going to leave as an exercise, this will be the first exercise really, to check that the rank of the derivative matrix is indeed equal to 2 for xy in K2. The rank may be not equal to 2 at other points. For example, if you take the origin, the rank of the derivative matrix there will certainly be 0. But on the zero set, the rank is constant at 2, that's maximal, and so the zero set is a good submanifold of K2. I beg your pardon, it's a good submanifold of R2, and we can transfer, we won't do it now, but later on, we can transfer that manifold structure back to the set of oriented lines in the plane and make that a manifold. And that's a manifold that isn't presented as the set of points inside some Rn. This works, of course, in 3 dimensions and indeed in any number of dimensions, and I'll ask you to do the case of 3 dimensions, oriented lines in space, as an exercise. So this is an interesting example. First of all, from a physical point of view, if you're going to do optics, ray optics, then the space you're working with is the space of rays in R2 or R3, let's say R3. That's effectively oriented lines. So this space, this manifold that we've produced, is indeed the space for ray optics in 2 dimensions and likewise in 3 dimensions. On the other hand, it's also a description of the cotangent bundle of the circle, and cotangent bundles are fundamental objects in symplectic geometry, and we'll say a bit about that at the end of the course. And indeed, these two things go together. The optics and the symplectic geometry belong together. Optics is historically one of the origins of the Hamiltonian formalism and therefore of the concept of a symplectic manifold. Okay, that's for another day. One more comment. What I've done here is taken an abstract manifold. Well, it's fairly abstract, it's not a set of points, and identified it with a submanifold of some Euclidean space. And there's a general theorem that any abstract manifold can be identified, can be embedded in some Rn as a submanifold. And that's a very deep result. We won't really make use of it, but it's a worthwhile thing to know. The general theorem, of course, doesn't produce a very useful concrete embedding. It's an existence result. What we have here is a specific embedding, which is takes account of the actual nature of the original set of oriented lines, and that's an important thing. Just the same, it's worthwhile knowing and keeping in mind that all abstract manifolds can be identified with submanifolds of some Rn. Okay, that's it for now.